Hello everyone. So today we will see the remaining portion of the periodic table, classification of elements. It's a simple chapter. So last class we were dealing with the making of periodic table and the long form periodic table by Mendeleev and the periodic laws, that is the earlier law as well as the modern law. And you know how to write the IUPAC naming of elements greater than 100. Okay. So now we will see the trends in the periodic table. What are the trends? You know, you have studied earlier, but still going into some detail, little more detail with the trends. That is, first is the atomic radius, atomic radii. Okay. So coming to atomic radius, you know, it is very difficult for us to have an exact radius of an atom. Why? Because the atom is very small and the radius is approximately comes to equal to 1.2 angstrom. That means into 10 raised to minus 10 meter. See, point, then 10, zeros, then 1. So you can imagine how an atom is, and it is very difficult to have an exact radius or exact radius of an atom. Okay, and also you know there is no exact boundary for an atomic for an atom. That is, it is not exact spherical. So you can't measure it exactly the radius. Okay, so it is difficult for us to have the exact measurement of the atomic radius. So then we will see how you can measure the atomic radius. We can measure the atomic radius by forming a covalent molecule. Okay, covalent molecule, and then you take the distance, half the distance between a covalently bonded molecule. Okay, that means, for example, if two chlorine atoms, for example, if this is one chlorine atom and this is another chlorine atom, it is covalently bonded by a single bond, particularly a single bond. Okay, not a double bond, single bond. So it is covalently bonded with a single bond. Then what happens? This you can measure it. Okay, so this internuclear distance is half of this will be the atomic radius. Okay, so this you simply call it as covalent radius, isn't it? So this is called as covalent radius. Why? Because you are bonded two molecules, two atoms covalently by a single bond. Okay, so this is simply termed as a covalent radius. Now, if it is a metal, you can measure it as a metallic radius. Okay, for example, if copper is a metal, so two copper atoms bonded together, and this internuclear distance, half of this internuclear distance in this metallic lattice will give you the metallic radius. Okay, so by bonding of two atoms, we can measure the atomic radius. Okay, so this is simply called as the metallic radius. Okay, in metals, metallic radius. Okay, metallic radius, and this is called as a covalent radius. Okay, so for example, chlorine atom, two chlorine atoms will covalently bonded together by a single bond. You measure this internuclear distance between these two atoms, then half of this will give you the radius. Okay, in the same way, the metal also, if two metal atoms like copper, okay, then the internuclear distance, half the internuclear distance will give you the metallic radius. But for our convenience in our textbook, we just refer not covalent radius or metallic radius, we just simply say it as atomic radius. Okay, you are not differentiating into the covalent or metallic, you just say it is nothing but the atomic radius. Okay. So this is about the atomic radius. Okay, now if you want to calculate the atomic radius of inert gases like helium, neon, argon, they are all monoatomic, right? Helium, neon, argon, krypton, xenon, all are monoatomic in nature. So here it has size, from top to bottom the size increases, isn't it? So it has got a size of its own, and for this thing you cannot calculate the atomic radius, you will calculate rather van der Waals radius, a molecule. So in this noble gases you calculate van der Waals radius rather than the covalent radius. Okay, van der Waals radius, that is molecule because it is monoatomic in nature. Okay, so this is about the atomic radius and the metallic radius, covalent radius. You both together call it as the atomic radii. Okay. Now we will see what is the trend in this atomic radii. Okay, in the periodic table, what is the trend in the atomic radii, or how you will go for the atomic radii from top to bottom in a periodic table or from left to right in a periodic table. Okay. You know, from left to right in a periodic table, or if you just say the hydrogen, lithium. So second period, lithium, beryllium, boron, carbon, nitrogen, oxygen, then fluorine, okay, then neon. Okay, so this is the noble gas. We won't discuss it here, but as you go from left to right in a periodic table, you know the atomic radius decreases, isn't it? The atomic radius decreases. Why? Why? Because in this along a period, what happens? The electrons are added in the same shell, isn't it? So this is the second period. So this is the principal quantum number is n is equal to 2. So second shell, one electron is getting added, isn't it? So what happens? That since the electrons are added in the same shell, what happens? The effective nuclear charge increases, isn't it? That is the point. So the effective, that is Z effective, increases, thereby atomic size or atomic radius decreases, isn't it? So there will be a greater attraction between the outer electrons and the nucleus, thereby the atomic radius decreases. So from left to right in a periodic table, the atomic radii decreases. Correct? Okay. Now, what happens when you go from top to bottom in a periodic table? So lithium, sodium, potassium, rubidium, cesium. Okay, francium you won't take into account, but still francium. So what happens? Here the atomic radius increases. How? Because the principal quantum number increases. N is equal to 2, N is equal to 4, N is equal to 5. So in all these cases, or in each cases, one shell is increasing, isn't it? So what happens? The atomic size increases, isn't it? So that is the trend of atomic radius. So while going from left to right in a PT, the atomic radius decreases. What is the reason? The Z effective, that is the nuclear charge, effective nuclear charge increases, thereby the atomic radius decreases. Correct? Now from top to bottom in a periodic table, what happens to the atomic radius? The atomic radius increases because in each cases the principal quantum number increases, or one number of shells increases, thereby the atomic radius increases. Okay, so that is about the atomic radii. Okay, so we talked about first the covalent radii. So you can, the funda is you cannot calculate exactly the atomic radii. You will go for a molecule, a covalently bonded molecule. You take the internuclear distance, half the distance will give you the atomic radii. Okay, because the atom is very, very, very small. So this is about the trend is left to right in a PT, atomic radius decreases, then top to bottom increases. Now we will see ionic radii. How ionic radii comes into effect. Okay. Same as the atomic radii, the trend is same for the ionic radii, which is seen in the atomic radii. So ionic radii means, how will you calculate ionic radii? Ionic radii you can calculate. For example, if you take NaCl, you know NaCl, it has got a crystal lattice. Okay, you will study in the 12th standard how this lattice occurs, and the distance between, for example, if this is an NaCl crystal lattice, you have Na here, okay, Cl minus is higher, bigger size, again this Na is smaller size. So the distance between these two, see, the distance between the sodium and the chloride ion, okay, this is chloride ion and this is the sodium ion. So the distance between these two, so this is sodium and this is chloride. So the distance between these two will give you the ionic radii. Okay, so that is ionic radii. And you know there are two types of ions. What are they? One is a cation and other is an anion, isn't it? One is a cation and other is an anion. Now what is a cation? Cation means an atom carrying a positive charge. So positive charges are called as cation and negative charges are called as anion. Correct. Now how a cation is formed? A cation is formed by the removal of electron, isn't it? The cation is formed by the removal of electron. For example, a simple example, you know, Na will give you Na plus plus 1 electron, isn't it? So this is removal of electron and forming a plus charge. Okay. Now what about an anion? Anion is for Cl plus an electron will give you Cl minus. So gaining of electron will give you an anion, whereas losing of electron will give you a cation. Okay. Now the next thing is, a cation will be always a lower in size than a parent atom. Okay. So board exam question, it can come like this. Why a cation is having a smaller size than the parent atom, as whereas an anion is having a greater size than the parent atom. For example, a simple example if you take as Na. Na is the parent atom. Okay. Now Na on losing an electron will give you Na plus, isn't it? So minus electron will give you Na plus. Now what I am telling is the Na plus ion has got a smaller size than the parent atom Na. For example, if you see the electronic configuration, it is 281 and this is 2A. So from this you can say here, by transforming into this Na plus, 1 electron is giving, so one shell is omitting. So the shell is decreasing, thereby the size is decreased, isn't it? Size is decreased. That is one way of explaining that. Okay, so here one electron is removing, so one shell, that is first shell, second shell, third shell is removing. Here only 2 shells are there, so the size decreases, isn't it? So the cation is always having a smaller size than the parent atom. Now one more explanation you can give. For example, if it comes from top to bottom, you can say this. Why? Because the shell is omitting. Okay, decrease in the shell, number of shells. But when you come across to a period, for example from lithium to fluorine, the cation size, for example Li plus, okay, Li, then Be plus, beryllium, boron plus, etc. That is cation. So in this case, from left to right in a periodic table, what happens? What happens to this cation? The cation, again, the cation size is lesser than the parent atom. Why? Why? Because cation means losing an electron. So there is a lesser number of electron. See, listen carefully. Lesser number of electron, and but the nuclear charge remains the same, isn't it? Nuclear charge remains the same, but from that nucleus a number of electron is decreased. So what happens? The outer electron will have a very high attractive force towards the nucleus. Thereby what happens? The size decreases. So two explanations you can give. One is, as the number of shells decreases, the size decreases. Thereby cation have always got a smaller size than the parent atom. Clear? Second explanation is, now how you can form a cation? By removal of an electron, isn't it? Now when removing an electron, what happens? In an atom, if you take an atom, what happens? In removing an atom, electron, it will form a cation. Now what happens? You are removing an electron, so the number of electron is decreasing. Thereby, what happens? There are only fewer electrons in the valence shell, and that electrons will be very much pulled by the nucleus. Thereby, the size decreases. So two explanations are there. Okay, you got it right? So that is why cations are always having a smaller size or lesser size than the parent atom. Now exactly the opposite. What is it? An anion will have a larger size than the parent atom. Okay, how this can be explained? Okay, now for example, if you say chlorine. Okay, chlorine, what happens? Chlorine will accept one electron to form Cl minus, isn't it? So this is an anion. And what it is said, anion will have always a greater size than the parent atom. That means Cl minus will have a greater size than the chlorine atom. Now how is it that possible? You know, chlorine atom, you know, 2, 8, 7, isn't it? 2, 8, 7, 17. Now if it accepts one electron, what will form? 2, 8 and 8. It will form the configuration 2, 8 and 8. Now here the logic or the reason is, now see, you have a chlorine atom, right? there are 7 valence electrons in its outermost shell. Now when one electron it gets accepted means what happens? There is a greater repulsion between the electron and the coming electron and the electrons in the outermost shell, isn't it? So if I draw a chlorine atom, see chlorine atom, first this is a nucleus, here it is 2, here it is 8, 2, 4, 6, 8 and here it is 7, isn't it? 2, 4, 6 and 7. Now what happens? If one electron is attracted or it is gained by a chlorine atom, what happens? This electron and the electron between them, because electrons are rotating, so electron-electron repulsion becomes higher. And what happens? Due to the electron-electron repulsion between these electrons, the size increases, or due to the repulsion, what happens? The size increases, isn't it? Or you can say due to the repulsion the size increases and the effective nuclear charge still remains the same, isn't it? There is no effect in this nuclear charge. Then due to the repulsion of this electron with the other electrons in the chlorine atom, what happens? The ionic radii increases. So there is a bulging out. Due to that repulsion, it gets bulged out. Okay, so that is why the anion is always greater than or having a greater size than the cation, due to the electron repulsion, the repulsion between the coming electron and the electron in the outermost orbit. So that electron-electron repulsion will make it comes little bit bulger, thereby the size of the anion increases. Clear? So this is about the anion and the cation, or the size of the anion is always greater than the parent atom, whereas the size of the cation is always lesser than the parent atom. For example, sodium or chlorine. Okay. Now we will say some atoms or ions have same number of electrons. See, some atoms or ions contain same number of electrons. For example, O2 minus. So oxygen is 8 electrons, isn't it? So 2 minus means, always minus means adding electrons. So 8 plus 2 electrons, that is 10 electrons. Okay. Then F minus. See, F minus. F minus means F is 9. So adding 1 electron, it will get 10 electron. Okay. Next is Na plus. See, Na is having 11 electron. So plus means 1 plus means losing 1 electron. So what will happen? 11 minus 1, that is 10 electron, isn't it? Next, if you see Mg2 plus. What is Mg2 plus? 12 minus 2, that is equal to 10 electrons. So see, all these species or all these ions or even atoms you can have. Okay. So what is 10? Neon atom, isn't it? Neon is 10. So atoms or ions having same number of electrons. See, even though it contains same number of electrons, what happens? Its radius is different, isn't it? The radius is different. See, that's very, very important. Even though it contains same number of electrons, its radius is different, because O2 minus radius is not equal to F minus radius or Na plus. It depends. Why it depends? Because the nuclear charge is different, isn't it? Nuclear charge is different. Because oxygen is having a different nucleus, fluorine is having a different nucleus, isn't it? So depending upon the atomic number, the nuclear charge is different, thereby the radius also is different. But the number of electrons is same. So such species where atoms or ions having same number of electrons are called as isoelectronic species. What is it? Isoelectronic species. So what are isoelectronic species? Isoelectronic species are those atoms or ions having same number of electrons. Clear? So these isoelectronic species have different radius because they are having different nuclear charge. Because the oxygen contains different neutrons and protons in the nucleus, whereas fluorine contains different, whereas sodium contains different. So different nuclear charge, thereby different radius, but it contains same number of electrons. So such species having same number of electrons are called as isoelectronic species. Now, in the case of an isoelectronic species, what I want to tell you is a greater charge in the cation. Listen, a greater charge in the cation, okay, a greater charge in the cation have lesser radius. See, what do you mean by that? A greater charge in the cation will have lesser radius. Why? Because for example, if you say Mg2 plus and Na plus, which is having a greater charge Mg2 plus. So, the size of Mg2 plus will be lesser than the Na plus. Why? Why? Because the effective nuclear charge increases. Because if you lose 2 electrons, what happens? The number of electrons in the outermost orbit will be decreased, isn't it? So, the attraction between that electrons, outer electrons and the nucleus increases, thereby the size decreases. So, as the charge increases, the effective nuclear charge increases, thereby the ions, the size of the ion decreases. So, greater the charge of the cation, lesser will be the ion, cation. Isn't it? So, that is the funda. So, greater the charge on the cation have got lesser radii. And what about the anion? Greater the charge on the anion will have greater radius. See, greater the charge on the anion will have greater radius. How will it be possible? How it will be possible? Listen, for example, if you have Cl minus and SO4 2 minus. See, this is having 1 minus charge and this is having 2 minus charge. Now what happens? If only 1 minus charge is there, then the chlorine is attracting only 1 electron and that electron will have a repulsion among this outer electron of the chlorine. But if 2 electrons are coming, the repulsion will be greater. If the repulsion is greater, the size will become greater. Clear? So, due to the repulsion between the electrons, the size increases for a anion. So, greater the anion charge or the charge on the anion, what will happen? Greater will be the radius. So, more and more electron is coming means repulsion is increasing, thereby the size is also increasing. Okay, there the nuclear charge has got no effect. Here only the charge on the anion, the repulsion is coming in front. Okay, or the repulsion outweighs the nuclear charge. Isn't it? So outweigh means it. Okay, that is why. So the greater the charge on the cation will have a lesser radii and greater the charge on the anion will have a more or greater radii. Okay. Now the reason is greater the charge on anion will have greater radii. The value point is what? Due to the repulsion between the electrons. Okay. Due to the repulsion between the electrons. Which electrons? The coming electrons as well as the electrons in the valence shell. Okay. As the number of electrons, coming electron increases, the repulsion increases, thereby the size increases. Whereas in the case of cation, greater the charge on the cation, that means electrons are losing from that atom. What happens? The effective nuclear charge increases because the electrons are losing. So there are only fewer number of electrons and that electrons will be tightly held by whom? Nucleus. Thereby the size of the atom decreases. So that is the reason behind it. Okay. So this is how logical questions comes and you have to answer logical reasoning questions. Okay. So this is the reason for that. Clear? Okay. Now we will see. So this is all about what? This is all about the ionic radii. So now we have studied two trends. One is the atomic radii. Atomic radii is having a similar trend as the ionic radii because as you move from left to right in a periodic table, the ionic radii also decreases. The same logic. Whereas from top to bottom, ionic radii increases. So similar trends in both atomic as well as the ionic radii. Clear? Now we will come to an important thing or the trend which is called as the ionization enthalpy. Okay, it is very, very important. That is ionization enthalpy. So I hope you are clear with the atomic and the ionic radii. Okay, as well as the isoelectronic species. Okay. Now we will see ionization enthalpy or ionization energy. Enthalpy is nothing but energy. Okay. Now what do you mean by ionization enthalpy? You know what are ions, isn't it? What are ions? Ions means positive ions as well as negative ions. Removal of an electron and gaining of electrons. Cations and anions. Now ionization enthalpy means, see, the definition itself says that the energy required, we are giving energy. Okay, that is why energy required to remove an electron from an isolated gaseous neutral atom. That is the correct definition for ionization energy or ionization enthalpy. Let me make it clear. For example, if this is an atom, any atom, but that must be in a gaseous state, not in a solid or liquid, but it must be in a gaseous state as well as it must be neutral. The criteria is it must be neutral as well as it is in the gaseous state. For such an atom, we are giving energy for what? In order to remove the most loosely bounded electron. Clear? In order to remove the most loosely bounded electron from a gaseous isolated neutral atom. So that energy, whatever energy you are giving, in order to convert this gaseous atom into an ion is called as ionization energy or simply ionization enthalpy. Enthalpy means nothing but energy. So if X is a gaseous state and it is a neutral isolated atom, you are giving energy to it and what happens? It will form X plus. How? By removing an electron. See, you can write like this or you can write X minus electron will give you X plus. Either way you can write. Okay, study one properly. So, in order to remove an electron from a gaseous isolated neutral atom, how much amount of energy is required? Required, that means this reaction is endothermic, isn't it? You are giving energy. If the energy was released, you can say it was exothermic, but here the energy must be given in order to remove an electron from a gaseous isolated neutral atom. That energy is called as the ionization potential or ionization energy or ionization enthalpy. Okay, we will call it as ionization enthalpy. Clear? For example, if I say Na in the gaseous state, you are giving some amount of energy, it will form, that is amount of energy is IE1. What is 1? First ionization enthalpy. That means in order to remove a single electron or one electron, that is called as first ionization enthalpy. So it will form Na plus plus 1 electron. Normally, since it's an energy, the unit is kilojoule per mole. Okay. So we will say it is the first ionization enthalpy. Okay. Now, what is second ionization enthalpy? Second ionization enthalpy means already you have an ion, Na plus, isn't it? So, next step is when from a positive ion, the removal of again an electron, second electron, that is why you call it as second IP or second ionization enthalpy E2. Okay, you can always say I1 or I2, anything, whatever according to your convenience. Okay, so and second, that is forming Na2 plus. So how much amount of energy should be given in order to remove an electron from an already positive ion? That amount of energy is called as second ionization enthalpy or second ionization potential or second ionization energy. Now tell me, which is greater? Whether I1 is greater or I2 is greater. That means first ionization energy is greater or second ionization energy is greater. What will be the answer? It will be second ionization energy will be greater than the first ionization energy. Now what is the reason? Why? Why? Because you see, in the case of first ionization energy, the energy required to remove from an isolated neutral atom. Okay, and it forms an Na plus. But what about the second case? it is already having a deficient or a plus charge, and from a positive ion, a removal of electron will be very, very difficult, isn't it? Because it is already a positive ion. So, in order to remove an electron from a positive ion, see, it must be very, very fully attached to nucleus, isn't it? Since it is a positive ion. Because it loses electron, so the electron is lesser, so the effective nuclear charge increases, so it will be having a very tight, closely packed, or having a very, very close attraction between the nucleus and the outer electron. So from such an ion, if you want to remove again an electron, that will be very, very high, or the energy required must be very, very high. So that is why you will say the second IP will be greater than first IP. Now what about third IP? Third IP means from a second 2 plus ion, the removal of again an electron to form a 3 plus ion. So it will be what? It will be very, very high, isn't it? So that is why you say I1 is less than I2 is less than I3, or I3 is greater than I2 is greater than I1. So that is the reason. So from a gaseous neutral atom, if you want to remove, it is okay. But from an ion, again removal of an electron will be difficult. From a 2 plus ion, removal of electron to form a 3 plus ion is still difficult. So I3 will be always greater than I2, which is still greater than I1. Okay. But if nobody talks about all these first IP or second IP or third IP, the definitions of IP, the default IP is what we call as the first IP. So in a question, if there is no conversations of this first, second or third IP, you have to select it as the default IP, that is the given first IP. Okay, so that is, if there is no reference, then you take it as a default IP, that is the first ionization potential. Clear? So that is about the ionization enthalpy or ionization energy or ionization potential. Now once again I will tell you the definition, that is the energy required to remove an electron from the energy required to remove the most loosely bounded electron from a gaseous isolated neutral atom. That is a precise correct definition for an ionization enthalpy. And second IP is always greater than the first IP. You know the reason. Okay. Now we will see. If you look at the trend of IP, okay, the trend of ionization potential, you have given a graph in your textbook. That is the first 60 elements, IP, ionization potential is drawn in a graph in your textbook. Okay. There, that is the second period, the first 60 elements they are plotting. Okay, the first 60 elements with their IPs, if they are plotting, you will get a periodicity in the graph. What is the periodicity? Like similarity in the graph. How? That is, there is a peak, then there is a dip, then so many elements, then there is again a peak, the dip, again a peak, dip, again a peak, dip. If you just refer to your textbook. Now, which says that all the peaks are for the noble gas, helium, neon, argon, krypton, xenon, etc. And all the dips are for alkali metals like lithium, sodium, potassium, rubidium, cesium, etc. So this was the similarity or the trend which you saw in the graph, which is plotted IP against these first 60 elements. Okay, which shows what? Which shows the higher IPs are for helium, neon, argon, krypton and xenon. Why? You know, these are all noble metals. Noble metal means octet. They have a fully valence electron, or they satisfy the octet theory, or they have a stable configuration, that is S2P6 configuration, except for helium, which is a duplet. So in a stable configuration or in a stable electronic configuration structure, if you want to remove an electron, that is IP, right? It will be very difficult because it is already a stable configuration. Okay, it is having a lesser energy or stability is there. So in such a situation, if you want to remove an electron from a stable configuration, you need a higher amount of energy. That is why all the peaks are for what? The noble gas elements. Helium, neon, krypton, argon. Now coming to the dips. Dips are alkali metals like lithium, sodium, potassium, rubidium and cesium. Why? Have you ever seen the configuration? What is the configuration? NS1 configuration. Isn't it? That is 1s1 lithium, then lithium, sodium, hydrogen 1s1, lithium 2s1, then sodium 3s1, like that. Which means what? Which means there is only one electron in the s orbital. Only one electron in the outermost orbital. Okay. And moreover, these electrons are preceded by, what do you mean preceded? That means in the penultimate shell, they are stable or they are fully filled core or octet electrons are there in the element, isn't it? So what happens? What happens? Then the charge between the outer electron and nucleus will become very less. That is, the effective nuclear charge will be decreased. And as you go from top to bottom, since the size increases, the distance between the nucleus and the outer electron also increases. Thereby, you can very well pull out an electron. So, ionization enthalpy decreases. Decreases down the group. Clear? Okay. So, this is about this ionization enthalpy of this dip in the alkali metals, because it is very, very low. Very low IP must be required in order to knock out only one valence electrons. Very low energy. But when you compare with this noble gas element, since it has got a very stable configuration, it is very difficult to pull out an electron from a stable configuration. So clear? Okay. Now we will see the trend in the IP. From left to right in a PT, what is the trend in IP? Whereas from top to bottom in a PT, what is the trend? So now you got an idea of how the IP goes for 60 elements, the peak and the dip, and what is the reason behind it, and what is ionization potential or ionization enthalpy. Okay. Now we will see the trends. Okay. What is a trend? The trend is, as you know, IP means you have to remove an electron. Okay. Now from left to right in a periodic table, if you say the second period, that is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. So in the second period, you know, as you go from left to right in a periodic table, what about the atomic size? The atomic size, listen, that's an interesting thing between the atomic size and the IP. The atomic size decreases. Why? Because the effective nuclear charge increases. Listen, if the atomic size decreases, means what? Decreases means the outer electron is very well attached to the nucleus, isn't it? Because it is very small. So when you go from left to right in a PT, the atomic size decreases. The reason is effective nuclear charge increases. Now coming to ionization enthalpy. What is ionization enthalpy? The energy required to remove an electron from a gaseous neutral atom, isn't it? So as the size decreases, what happens? The valence electrons and the nucleus, the attractive charge or the effective nuclear charge increases. Thereby, it is very difficult to pull out a valence electron from a atom. So you can say what? The IP increases because it is very difficult, because the size is very, very small. So it is related to atomic size, isn't it? The IP is related to atomic size. Now, so is it clear? So since atomic size decreases, IP increases. Why atomic size decreases? Is that effective increases. Nuclear charge increases, isn't it? So these are the points or the reasons behind it. Now you come from lithium, sodium, potassium, rubidium, lithium, sodium, potassium, rubidium, cesium and francium. What happens to IP? Since the atomic size increases, why atomic size increases? For every period, the shell increases. Now as the shell increases, what happens? The size increases. When the size increases, what happens? the distance between the nucleus and the valence electron increases. Thereby, what happens? The IP decreases, because it is very easy to pull out an electron, or very little amount of energy must be required or to given in order to remove an electron from that gaseous neutral atom, because the size increases. Isn't it? So that is the reason behind it. So from top to bottom in a periodic table, the IP or the ionization enthalpy IE, what happens? Decreases. And if you go from left to right in a PT, the IP increases. Clear? Now, this much you have studied in the 10th standard, isn't it? Now what happens is, if you go into some more details regarding the electronic configuration, you know, for example, if I say simple case as lithium. Now is it clear? Okay. Now if I say lithium is 3, atomic number is 3. Okay. Now if I draw it, okay, it has got nucleus is 3 proton and 3 neutron. The first shell is 2 and the second shell is 1. You are remembering the sp notation? 1 is 2 and 2 is 1. This is the electronic configuration of lithium. Now what happens is, listen very carefully. The effective nuclear charge, you know what is effective nuclear charge? The effective nuclear charge which is experienced by the outer electron. Listen, the effective nuclear, this electron, we are talking about this electron. See, we are talking about this electron, the valence electron. Now the effective nuclear charge which is experienced by this valence electron will be lesser than the actual nuclear charge. That means the actual nuclear charge is +3 for lithium, isn't it? But the nuclear charge which is experienced by the outer electron will be lesser than the actual nuclear charge, that is +3. It will not be +3, but it will be something lesser than +3. Why? Why? Because due to the shielding effect. You have studied the shielding effect in quantum mechanics, isn't it? What is shielding effect? These inner electrons will shield these outer electrons from the nucleus, isn't it? So what happens? Thereby the effective nuclear charge will be decreased. That means if exactly the +3 is the nuclear charge, the outer electrons will not experience the full +3 charge. Why? Because the inner shielding effect, the shielding effect of this core inner electrons. And when will be the shielding effective? The shielding will be effective when the preceding shell, that means the penultimate shell, will have an octet configuration. Listen, when it is a fully filled shell, the penultimate shell is a fully filled shell, and the outer electron will experience more or greater screening or shielding effect than the other cases. Okay. So in the case of this lithium, this 2s electrons will have a shielding effect of whom? The shielding effect of this 1s electrons. And you know the maximum number of electrons for an s orbital is 2. Isn't it? So there will be a greater you can also say screening effect. Okay. So shielding effect, greater shielding effect of this s electron, 1s electrons for the 2s electrons. So what happens then? Then since the effective nuclear charge decreases, you can very well remove this electron, isn't it? You can very well remove this electrons because it is not getting the full nuclear charge. Okay, so that is the reason behind the screening effect. Now when an IP question is asked, ionization enthalpy is asked, you have to relate both the screening effect as well as the removal of electrons. Both you have to take into consideration. So now you know what is screening effect. Okay. In the case of lithium, it is screening, and the screening effect is much pronounced when, or it is effective when the penultimate shell has got a octet, a filled octet. Okay, filled electrons. Okay, so that is the screening effect. Okay. Now, we will see what happens the trend in IP when you consider both the screening effect as well as the removal of the electrons. Okay, you will see that. Now you got screening effect, right? Okay, you have studied that. Now, when you consider the second period again, that is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. In the second period, what happens to the IP? Okay, you have to account the IP in screening effect also. Now, you know from left to right in a periodic table, we told that the IP increases because the atomic radius decreases. Now, what about the screening effect here? What about the screening effect? See, in this second period, that is in the second shell, okay, this is the second shell. Lithium has got 1 electron. Now second shell, beryllium has 2 electron. Then boron has 3 electron. Carbon has 4 electron. Likewise, 1 electron is added up into the same shell. Listen, 1 electron is added up in the same shell. Then what happens? Here, the effective nuclear charge is same, because the effective nuclear charge means what? The effective nuclear charge increases. And here the screening effect has got not much effect when compared to the effective nuclear charge. Listen carefully. In the case from when you come from left to right in a periodic table, the IP increases. Now what is the reason? You have to put the screening effect also into account. Now when the screening effect as well as the nuclear charge, both you have to take. And what is more, then that point you have to write. Okay. Now from left to right in a periodic table, the IP increases because the atomic size decreases. Okay, atomic size decreases. Listen. Atomic size decreases means what? In the second shell, 1 electron, in the same shell the electrons are getting. So what happens? The effective nuclear charge has got a greater effect than the shielding effect. Because here the shielding effect remains the same. The penultimate shell remains the same. Only the outer electrons, one electron is adding. That's all. So here what happens? More than the screening effect, what will come? The effective nuclear charge comes. So due to the increase in the effective nuclear charge, the IP increases while going from left to right in a periodic table. That is the formula. Clear? Okay. Now what will happen from top to bottom in a periodic table? Listen. Top to bottom in a periodic table, what happens? The number of shells increases, isn't it? Now what happens? There, the effective nuclear charge has got less effect when compared to the shielding effect. Because when you come from top to bottom, you know what is the configuration? NS1 outer electronic configuration. What will be the penultimate shell? It must be an octet, isn't it? Octet or a complete shell. So since there is a complete shell, here the shielding effect will be much pronounced than the effective nuclear charge. That's it. So is it clear? So that is the remaining IP we will see in the next session. Okay. So just go through the textbook. Thank you.